Hello everyone, and welcome back to our reading of categories and sheaves. We pick up now in chapter 2. We've made our first sort of landmark progress, and now we get to start really getting into the meat of the book. Well, hopefully. It may not feel like it for a little while, but nevertheless, starting in this chapter, we get a leg up in the level of generality. And so let's just sort of start turning those ideas over. All through chapter 1, we have employed commutative or sometimes quasi-commutative diagrams in order to sort of be a bookkeeping device, something that allows us to keep track of all the maps that are involved, or in the level of categories, all the functors involved, and make sense of what it means for diagrams to commute. But now we need to sort of generalize this in order to talk about limits at a sufficiently high level of generality. So we're going to do that, and the primary difference is that now we're going to talk about diagrams as small categories. Or maybe I should say as functors out of small categories. But I'm going to write what I started writing. So maybe what I'll write is diagrams or shapes. And this was definitely something new to me. I've never really seen this until now because I'm not a category theorist at heart. So let's see if we can unpack what's going on here. So Kashiwara and Shapira use letters I, J, K to represent small categories. And there's this business of universes and all that learning in the background that they sort of remind us that we never think about this, so we're not going to think about it. And what you should do is think of such a category as a blank diagram. And what that means is that it's basically a diagram where you've got a bunch of objects, maybe like this, and morphisms between them. And we haven't yet filled them in with anything. And then a functor from a category that looks like this to some other category like sets amounts to picking some objects that we could plug into these dashes and actually obtaining a familiar diagram. So an ordinary commutative diagram should be thought of then, according to Kashiwara and Shapira, as a small category which tells us the shape together with a functor to some other category telling us the objects, like the actual entries of the diagram. I wrote entry, but entries. And with this in mind then, we can rephrase everything we've done so far in terms of diagrams, now in terms of functors. And if this seems weird to you, well, maybe it's not that crazy, right? I had myself a sort of long think about this and try to understand what's going on here. And it's really not that bizarre. Like when you first take your analysis class for the very first time, like you learn about sequences. And when you have a sequence, you write the elements like x lower n. But what's a sequence? Well, the definition of a sequence is a map from n into some set, like the real numbers or a metric space or whatever, where you would send n to something like x of n, but we don't write that. We write like x little n. And you could, if you wanted to be really pedantic, you could even write like x as a function, which eats natural numbers and returns these things. But we don't ever do that. We just abuse the terminology and conflate a function and its image. And that's really what we're doing with this business of diagrams is, we're abusing the lack of distinction between a functor out of a small category and the image of said functor as actually being the diagram. Okay, with that aside, we're ready to start thinking about limits and colimits. But we're not going to call them that too often for at least a little bit, and I'll say more words about that in a bit. So we start with a category C, and then we call a functor, we'll use letters alpha, beta for these, from I to C. This will be called an inductive system. And if we replace I with IOP, so maybe we do beta iopticity, then this will be completely the same. We call this a projective system. And if you've heard of this before, then I'll sort of say some words later on in the video about what this has to do with the ordinary ideas of inductive or projective systems that you might be familiar with. Maybe you already see it, but I'll elaborate anyway. And in order to set up the machinery that we're going to want for the video and for going forward, we'll start with projective systems. And in particular, we're going to start with projective systems that map to sets. So for now, we'll consider projective systems from small categories into set. And the primary way that we're going to sort of springboard ourselves forward to the general theory will be the unity dilemma. So let's start with some projective system, beta iop to set. And we're going to denote with star a category with one element and one morphism. And we're going to abuse this notation also, and also use it to mean a constant functor. And hopefully this never causes any confusion. In practice, when one wants to be interested in these sorts of things, there's only one map to a category with only one element, or I should say one functor from a category to one element, just like there's only one map to a set where there's only a singleton. And similarly, when I want to evaluate such a thing, then there's only one way to evaluate a constant. Sometimes when absolutely necessary, I might use some extra parens to indicate when I want to think of star as eating an object. So when I want this to be a constant functor, then I might be really clear and use some parens. But I think this won't cause any confusion going forward. So with this in mind, what you should realize is that star, being a singleton in sets, turns the functor star into a terminal object. That's a really cruddy star, but star is terminal in the pre-sheaf category for this reason. Just like star as in set is terminal among sets, star is terminal in the world in the functor category. So now we're ready to define a set, which we're going to call the projective limit, and we define it as follows. It's denoted by lim with a backwards pointing arrow, and the projective limit of beta is defined to be hom in this pre-sheaf category. We're interested in pre-sheaves of sets, but I'm just not going to write that. Star to beta. And of course, remember, this is all happening in a functor category. So to unpack this, you have to think of star as a constant functor out of our diagram shape to this singleton. And then we're looking at natural transformations from this constant functor to beta, and the set of such natural transformations is our projective limit. That might be a bit much. So let's unpack this by sort of looking at what we get when we have evaluations. So I can consider hom star beta, and I can get a map in hom set. Sorry, let me write that this way. Maybe I should index this and say this is hom in pre-sheaves. In hom set by evaluating this guy on some I that belongs to the indexing category I. And when I do this, this is just the same thing as, of course, evaluating this. I just get my singleton again, and this is beta I. And then the question is, well, what is this? Well, the maps out of a singleton into beta I, those are just canonically just the beta i's. So what that does is tell us that we have a map from the projective limit of the betas, and sometimes I might write lim I and I, beta I, if I need to be really clear. At the moment, I don't think that's the case, but for the sake of making some nice symmetry in the notation, I'll put it in. Gives us a map into the product, and this is a product of functors, but we're again sort of abusing everything with its image, and we're thinking of this as happening in the world of sets. So this is a product of sets, basically. And we'd like to identify this limit with some subset of the product of these evaluations. Like we want to just sort of continue this abuse that we're going to carry out. And so in order to do this, we have to do more than just look at this map. We need to impose the relations that we get from the category I. And so when we do this, what we obtain is that the limit of beta should be identified with those tuples, which I'll call xi, which live in the product of the beta I, that satisfy beta of s applied to some xj equals xi for all s in Hom, now in I, between I and j. And this sort of looks like our familiar limit. And there's no problem with this definition either because, well, our sort of set theory assumptions sort of ensure that everything here is a set, and we're prescribing this according to some equations, so some set theory business should tell us that this is fine. Okay, now let's prove a prototype of a big result to come later. I feel like every one of these videos should contain at least a couple, like a proof or two, so let's do a prototypical result. So suppose we have a functor beta, I opt to set, and of x just any set. Then we have a natural isomorphism from Hom set x, and we take the backwards limit, and then over here we obtain the backwards limit of the Homs. And in case it's not completely clear, the right side Hom indicates the functor which takes I to Hom set x beta I. Okay, and how do you see this? Well, it's just sort of a matter of unraveling the definitions in the right order. So what are the elements on the left? On the left, we have set maps x to this limit. And by what we just said, these are maps into a subset of this product that obey these relations, the compatibility conditions in the arrow from the arrows of I. And on the right, well, we start with all the maps and we're going to take the product over these guys and then impose on them the constraints from I. And the definition that we just wrote above tells us that this is fine and that we're going to obtain the same objects either way. And of course, the naturality is, well, this is basically obvious. It just sort of means that if I want to compose with some other morphisms, then everything is fine. And this is just sort of clear from the definition. Now, I'll put a little box. We also have some ability to compose for these limits. So if I have a phi, some functor, j to I, and between two small categories, then I can set up the opposite functor, phi op, j op to I op. And then since I know that this limit here, the projective limit of the betas, this is just, of course, Hom star beta, then I can precompose with phi op, and this gives me a morphism beta composed with phi op. And we're going to see this sort of later when we're going to talk about what is basically reparametrizing, or maybe resequencing, if you like. So what you should do is basically think of this as happening like a filter. Like if I was thinking about sequences, then whatever this map would be for a sequence, it would be sort of like picking out a subsequence or re-indexing in some suitable way. The sort of catch is that these sequences or these systems are maybe more complicated than just the completely linear thing that you have when you're working with natural numbers. But the idea is sort of the same as passing through this restriction that we get from phi. Okay, so we continue. Let's make some general definitions now. We've sort of said everything we need to say about the basic objects in set, so now we're ready to make our general definition. This is going to be sort of a lot. We're going to come in some parts. So first, we define injective and projective limits. And the injective limit, we'll write with the forward limit of something alpha, will be x, and we're going to define it in terms of the projective limit of this will happen in whatever category we're interested in now, alpha x, which is the same as the projective limits of hc of x composed with alpha. And similarly, we define the backwards limit. I'm going to continue to call them this even though they're the injective and projective limits. X to the projective limit c x beta, and maybe it's completely clear where we were going with this. This will be kc x following beta. And if these functors are representable, then this is sort of the familiar case where this limit is somehow computable. And what I mean by computable in this case is that the representative actually lives in C. So what we'll do is we will abuse notation and also call the representative, even though maybe the way I say this is, even though this lives in some functor category, we call the representative also either the forward or backwards limit, whatever it may be. And basically this just means that we can find an actual object in C that corresponds to the object in the pre-sheaf category defined above. It's sort of important that we think about this because we can pretty much always do this in the pre-sheaf category, but these functors don't have to actually be representable. You don't have to actually be able to construct these things in whatever the category is beyond set. And then finally, if we have for every alpha from any I to C that lim alpha is representable, in other words, for all possible diagram shapes, all these limits are representable, then we will say that C admits all limits, or more simply is complete. And mutatis mutandis, if we do the same thing with betas I ops to C, then we'll say that C admits all colimits or is co-complete. Yeah, that's right. Okay. And this definition then completely agrees with the one we gave for projective limits the first time when C is sets. This is just sort of on the nose. We're not really doing anything with our Unita functor when we're already in sets. On the other hand, this Unita functor lets us sort of springboard from sets to a general category. I said when I was giving this definition that we'll call these things the forward and backwards limits. Well, we might call them limit and colimit. But for now, I want to either stick to calling them projective and injective, or I'll just call them forward and backwards because of the way the arrows point. And this is, for me, much easier to remember. I hope this doesn't annoy any of you guys, but I prefer this because the injective limit, well, it points forward, so it's going into the expression that follows. and the projective limit points outwards, which sort of I think of that as projecting away from it. And I just think that this makes it hard to get confused about which one is which. And if I start saying limit and colimit, then there's a good chance that I will make that mistake at some point. So let's show a couple of quick advantages to this level of abstraction. There are a handful of facts that this sort of thing makes obvious. So we'll call these consequences. And first, if I have a functor, alpha, from I to C, then alpha op, the opposite functor, I don't need to write it out again, we know how this works. Then what I see from this is that I have a natural isomorphism from the forward limit of alpha, which I take the opposite of, and simply the backwards limit of the opposites. And this is sort of completely clear from the definition. This is how Hom plays with ops. And this is our duality principle again, basically. The advantage to this is that when I want to prove a general theorem about either injective or projective limits, I only have to work with one of them, because if I address this, then I can just take opposites and I get all the same facts for the other. So I'll say this as the duality principle is compatible with colimits. Co/limits. That's like shorthand for colimits or limits. Okay, next consequence. There's no difference between an inductive system indexed by I and a projective system indexed by IOP. And this is feels like it's sort of related to what I just said. But it's sort of a consequence of our definition that if I reverse all the arrows in I, well, that's just the same category as IOP, but it's also what you get when you look at a projective system because that's the definition. Okay, and finally, we have a nice compatibility, which is that when these guys are representable, then we have Hom in C of a limit, of an injective limit, is the same as a projective limit of Homs. And completely similarly, Hom C of a projective limit is also the same as a projective limit of Homs. And just pay attention to the entries. And when you see that, this is basically just a consequence of the co and the contravariance of the Hom bifunctor, right? So if I wanted to unpack this, in fact, we sort of already said how this works for projective limits in set. Well, now our general definition via UNITA tells us that it's exactly the same, except when I do this in the first argument, well, then the contravariance says I have to flip the injective into the projective limit. Okay, so to end this for the day, I want to say a couple words about what this has to do with the sort of familiar diagrammatic version of limits and maybe colimits that you might have seen in an algebra class. And so let's just sort of say how we get from this abstract definition to the sort of diagrammatic or maybe graph-like definition in terms of compatibility conditions that you may have seen. And of course, to do this, we have to talk about the case when we're dealing with actually representable objects. So let's just go ahead and deal with injective limits and assume that the injective limits of some alphas are representable. And if I do this, then let's let the limit be y. So we'll just write this as lim alpha equals y. Then we can look at this particular set of Homs. We can look, or maybe I should say we can look at the injective limits of the Homs. and all this is happening in some category, but I don't care what that category is, alpha to y, well, by what I just said, that this is this should, oh, now I'm actually a little bit worried. Maybe I should be flipping this sign. Because I put this in the first component, so this would have to be then this way. So maybe I need to change. Maybe I need to change this so that I'm dealing with a projective limit instead. I don't think it matters for what I'm about to say, because if I flip it the other way, well, all the arguments I'm making are supposed to be sort of symmetric in injective versus projective limit anyway, so let's not worry about it for the moment. But what this buys me is y, which is of course never empty because it always contains at least the identity hom. And if I take the identity hom, then I can look at what happens in this limit when I choose that. And in particular, with this, I get a family of morphisms. So what are this family of morphisms like? Well, they're indexed by I, so I have these row i's, and they have the property that they map from alpha, maybe I call it alpha of I rather than alpha sub I, and they map to y. And they have to satisfy whatever conditions we get from I. So in particular, row j composed with any alpha s better be the same thing as row I for any s from I to j in I. And this is just sort of a restatement of the construction that we gave above when we said what the compatibility conditions are in the world of set. It's all exactly the same. So what we end up with here is a picture that looks like this. So we end up with these triangles where we have alpha I, alpha j, and these things all map to y, which is the limit. And I don't know what I'm going to call these. These should be the row i's and row j. And then here, this is just the image of whatever s is in I. And in particular, we can get the universal property also, because if I have any other bunch of maps to some other object, maybe I'll call it x, then I should be able to produce a map like so. And how does this construction come about? Well, this is basically just the same fact for products. We haven't talked about products yet, so I can't use that. How do I see this? So if I have some family of maps here, we'll call these fi, fj, all mapping to some x, then I always have the row i's. And why does this factor through? I see. This is because this family of morphisms that I give here, this is nothing else but a element of the limit of the homs into x. But in particular, if I have such a thing, then it implies, maybe I call this f in here, is just some collection of these fi's. But if I have this, then this gives us an element in the limit itself, which is just hom yx. And that element has to be unique just by this construction. And so that establishes the universal property. Yeah, I'm still thinking that I need to worry about this business of which way the arrow goes. This limit out here should become a forward limit in there. Yeah, so this is right now. Because now when I pass this inside, I get the forward limit of yx, which is what I want, the alphas, which is y. That's what I want. And maybe we abuse this notation. We also call this f. F in here is a tuple. And f in here is a particular element. Okay, so that establishes the universal property, and that tells us why this version of limits coincides with the old version of limits that we gave maybe back in your algebra class. Okay, next time we'll talk about the relationship between limits and adjoints and a few other useful properties. In particular, there's a theorem which is that right adjoints preserve limits. And of course, there's a completely dual theorem for left adjoints and colimits. But we'll see this next time. And then after that, if time permitting, we'll move on to seeing examples, of which there are a great many. I sort of regret not doing that section first. But in order to sort of employ the level of generality that Kashiwara and Shapiro want to give this at, it sort of feels unavoidable. So if you've never seen this before and you're completely feeling lost, well, I'm sorry. Just bear with us for one more session of abstract nonsense, and then we'll have many, many concrete examples on hand. And hopefully that'll begin to tame the zoo of craziness. Okay, see you next time, guys.